if you take away only one thing from this video, make it this. Hello Internet, my name is Quinn and this is Blondihacks. Today I'm going to talk about digital readouts or DROs. People are always asking me, how do you set one of those up? How do you use them? Are they worthwhile for hobbyists? Let's find out. You've no doubt seen these hanging off the back and sides of the machine tools of the cool kids, and they're not just there to make it look high-tech in that 1980s sort of way. There's two main components to the DRO, the control unit here, and some number of scales mounted on the machine. Ideally, you'll have a scale on each slide, so for a mill that's going to be 3 or 4 if you include the quill, and for a lathe that's typically going to be 2, the cross slide and the main carriage. But you may have fewer than that. For example, on a mill, the X and Y are by far the most useful scales, so especially on older DROs, you may have only those 2. And then there will be a mess of cabling that connects each of the scales to the control unit. Now when you see them on the machine, they just look like a featureless aluminum bar, but this is actually just a chip cover. So under here you can see the business end of it. Getting low down here, we can see how it actually works. On the moving section of the slide, we have this aluminum channel here, and up inside this channel is a scale. Nowadays it's going to typically be a glass scale that has a photographically printed pattern on it that's read by an optical sensor. In the old days this might have been a magnetic scale. And then on the stationary part of the slide you've got a head here which reads the scale. So this is where the optical sensor or magnetic read head is going to be. So you can see as I move the table that the scale moves with the table, but the sensor remains stationary, and then you can see the cable coming off the sensor that goes up to the computer. If you're looking to buy one of these, and you can get them direct from China very cheaply on eBay, there's really just 2 things to look out for. First, all of the buttons on the front, make sure that it's going to have all the features that you want, and you can tell by examining grainy photos on eBay if they're all here. And then the scales themselves, and this is really where the differentiation is in the different kits. The kits will have different lengths of scales, different quantities of scales, and different resolutions of scales. Length and quantity are obvious, make sure you have enough of them and that they're going to be long enough to cover the travel of your slides. So that just leaves resolution, and here there are 2 types, 1 micron and 5 micron. Any modern import DRO, the scales themselves are always going to be metric. If you're on a machine and wondering what the resolution of the scales is, just put it in metric and look at the last digit, and then move the table the smallest amount that you can. And you'll see that this machine has 5 micron scales in it because, well, they're going up by 5s. Typically the 1 micron scales are only a little bit more money, and if it's in your budget, I do think they're worth it, especially if you're going to be using the machine in Imperial. And the reason is that, as I said, the scales and also the software are all operating in metric, so when you're running in inches, it's just converting those values for the display. It's putting on a show. And of course, microns are never going to convert evenly into inches. This digit here is whole inches, and this digit here is your thousandths. And then this is your tenths, and this is 100 thousandths, or 10 millionths, as they're sometimes called. And this last digit in particular is going to be pretty fictional, because this is where all of the rounding is going to happen when it's converting from microns into inches. Maybe sometimes this digit as well. If you're into the 1s and 9s here, then this digit can be a little suspect as well. But this last digit especially, you really got to take it with a grain of salt in Imperial. But this is true of metric as well, because this is a 5 micron resolution, so anywhere between 0 and 5 microns, this last digit might read 0 or 5. But in Imperial, you have the additional unknowns of rounding, and you don't know how many significant digits they're using in the FPU for this conversion, or who knows, maybe they're even doing it in fixed point. You don't know anything about the software doing this conversion. So I treat this last digit kind of like a cat. It looks nice and seems useful, but you'd never really know what it's going to do. If your machine didn't come with a DRO and you're trying to install it, then what you need to do is find a convenient place on the split line of each of your slides to mount the scales and the sensor. So in the mill, this is usually pretty easy. Just find a flat spot on the back of the table and then, mount the sensor down underneath there. The key here, though, is that the scale needs to run just as true relative to the sensor as the table runs relative to the base of the mill. Now, some mills may have curved castings on the back or otherwise make it difficult to achieve that, but you can compensate for that sort of thing by, for example, mounting the scales on studs that have nuts on either side that let you shift the scale this way, and you can use slotted or oversized holes to shift the scale this way as needed, and then run an indicator down the top of your scale and make sure that it runs just as true as the actual table does. And then same thing for the sensor. If you can't make it perfect, make it adjustable. So mount this on some sort of studs or something that will allow you to shift it around a little bit and adjust the angle as needed so that it runs cleanly within that slot all the way down the length. Now, when choosing your mounting location, obviously you want to choose somewhere that's easy to mount it to. However, check that it's not going to be in the way. For example, on this mill, it's mounted on the back of the table, which was convenient because it's not going to be interfering with any controls here. However, being on the back, it does cost about 1 inch of Y travel because the table is going to hit the column sooner than it would if the DRO wasn't there. In this case, there was no choice. There wasn't anywhere to put it on the front, but consider that depending where you put it, it may cost you travel. And I'm not going to lie, there have been times when that inch has caused me to express some adult language. The table slides are pretty straightforward, but the Z slide can be a little trickier. Now on a column mill, it's pretty easy. There's usually a big column to mount it on. On something like a Bridgeport, a knee mill, however, you might be dealing with curved castings and, there might not be an obvious place to put it. Those machines predate DROs quite a bit, so they were designed without mounting one in mind. But once you've chosen your locations and your mounting hardware, then it's just a case of drilling and tapping into the castings. And if you're worried about drilling holes in this big, beautiful Wells Index or Cincinnati mill that you just bought, you can always patch them with JB Weld if you do it wrong, touch up the paint, or the holes are likely to be under the DRO anyway, and hey, I won't tell anyone if you don't. The lathe is usually easier. You've generally got plenty of room on the back of the ways for the main carriage slide, and then you just pick whichever side of the cross slide is going to be easier or less in the way. Okay, let's learn how to use this thing. One of the interesting side effects of Chinese electronics markets is that they have created de facto standards for user interfaces in electronics. So you can go and buy 10 different Bluetooth speakers and they'll all have the exact same controls, and this is why. And so it goes with DROs. As far as I can tell, there's 2 different board sets for these coming out of Shenzhen. One of them says ABS here, and one of them says ALE when it's in the absolute mode. So that kind of tells you which one you have. So those 2 board makers are selling those boards to control unit makers, and a bunch of those control unit makers are reselling them to other companies that are branding them and packaging them up with scales and selling them on. But that's good news for us because I can show you how to use this one, and it's likely very close to how yours works. If you're new to machining, a reasonable question would be, what is the DRO actually buying you? Sure, it shows you motion of the table, but so do the hand wheels, so what's the big deal? The big deal is that the scales are mounted directly on the slides. They're measuring motion of the table directly. The hand wheels, while they have markings on them, they're inferring motion of the table from rotations of the lead screw. So what that's doing is introducing an additional layer of mechanical abstraction between the measurement and the thing you're measuring. All mechanical systems have backlash in them. There's a lead screw and a nut down there, and you're measuring the backlash of that system in addition to table travel. So I can turn this hand wheel to there, and now I can feel it has engaged that lead screw nut in the other direction. And now I'm measuring table travel. And if I go back the other way, nothing, only now am I measuring table travel in the other direction. So every time you change direction with the hand wheel, you have to account for that backlash. Now look at what the DRO does. You can hear from the power feed gears in the background there that I'm wiggling the hand wheels back and forth, and the DRO is not moving because the DRO knows that the table is not moving despite wiggling around within that backlash area. So this is the big win for the DRO. It basically gives you hand wheels with 0 backlash. So as I take up the backlash, the numbers aren't changing until I engage the lead screw. Now the table's moving, now the numbers move. But don't be fooled by the computeriness. It's still measuring relative motion, just like the hand wheels, not absolute position. That's actually a good thing though, because what that means is we can use the zeroing to set an origin or a reference point anywhere that we want. So you can set up a part with an edge finder or whatever, zero out your axes, and now you can always get back to this spot. So this is equivalent to zeroing your hand wheels, but much more precise and much more useful because this is independent of direction of travel, unlike the 0 on a hand wheel, which depends on you having taken up the backlash before you get to it. So one of the most common things you'll do with the DRO is use a tool like an edge finder or a dowel or an indicator or other methods to find a specific feature on your part that you want to reference from. And then once you've got that all set up physically on the table, now you can zero that out. And from here, you can move around your part with reckless abandon, putting features relative to this origin however you need to, and you can trust that they will always end up in the right place because there's no backlash and this is very precise. But wait, there's more. There's actually 2 coordinate systems. If you take away only one thing from this video, make it this, the absolute and incremental button. Switch that and now you're in incremental mode, and now you have a completely separate second coordinate system for all of your axes. This is incredibly useful because usually your absolute 0 is something that you want to preserve for the length of your setup. Once you've got that part set up, you're going to want to move around it doing various operations on that part, and you never want to lose that absolute 0. However, when you're forming a specific feature on that part, you'll use the absolute to get to where that feature starts, but then let's say you're cutting a slot, that slot is going to have a certain width and you need to do multiple passes. You want to keep track of how you're doing along that feature. And you can do this with the absolute scale. You just have to do a bunch of math and that's error prone, or you can just switch over to incremental, zero this out at the start of your feature, and now this allows you to track your progress on that feature. That's just one example of how incremental is used, but it's incredibly useful to just be able to jump over here anytime, set a new 0, do some stuff, go back to absolute, and know that you haven't lost your true origin on your part.
Now let's look at some of these more exciting looking buttons on here, and there are a lot of them, and there's a simple reason for that. Once you have reliable tracking and you've got a microcontroller in the loop, then all of this other stuff becomes really easy, so you might as well do it. The simplest and most used, at least for me, is probably the half function. And what this does is takes the value of any of your scales and just cuts it in half. And that might seem of dubious value. Why would you ever need to do that? But what it allows you to do is find the center line of things. Let's say I want to find the center line of my part along the y-axis. So I use my edge finder. I find one edge of my part, and then I zero that. And then I find the other edge. Then I select my y-axis, and I have it, and there's half of the y value. Okay, well, great, Poindexter, obviously, but what good is that? Well, the superpower is if I now go back to 0, or as close to 0 as we can get with that imperial conversion that we talked about, but this is now the center line of the part. So this 0 line is right between those other 2 readings on the center of the part, because we went from 0, then to the other side, and took half of that, and now we're in the center. It's a simple trick, but surprisingly powerful, and it's something that you do really, really often, because the center line of a part is very often a reference for all the features on that part, since most mechanical parts are symmetrical on one or more axes. Second most powerful function is bolt circles, or maybe that's for navigation, or maybe when frozen it moves the island. But bolt circles are quite challenging to do without a DRO. Traditional methods for making bolt circles vary, but they generally involve first locating all of the holes, and you can do that based on the chord of the circle or various other algorithms and formulas that you can look up in the big book. And then you have to either lay out those holes or locate them all using hand wheels and very careful management of backlash. But of course, the bolt holes are in a circle, hence the name. So as you pass through each quadrant, you're changing direction in either X or Y. And as we've learned earlier, anytime you change direction, managing backlash becomes quite challenging. So doing bolt circles with traditional methods can be quite challenging, and to do very well can require a lot more skill than frankly I have. But there are other methods as well. For example, you can use a rotary table or a dividing head. But this $100 piece of Chinese electronics replaces both skill and entire expensive fixturing tools. We can just push a couple of buttons, we can rotate a bolt circle of any number of bolts, position it anywhere we want on our part, and it guides us to each hole. Bob's your uncle. So easy, even a hobbyist can do it. Let's do a sample 6-hole pattern here on a 1/2-inch radius. So you're going to start by positioning the center of the circle on your part. So I'll move my table over to wherever the drawing says the center of my pattern should be, and let's put it at 300, -300. Then press the bolt circle button, and the first question it's going to ask is for the coordinate plane that you want, and normally that's going to be XY, the plane that your bolt circle is going to be in. But there are other options. For example, if the head on your mill was rotated, you could do a bolt circle in the YZ plane on the end of your part. But I'm happy with XY, so I'm going to push enter, and now it's asking us for the center position of our circle. And this is relative to where we are right now, so typically 0 is going to be what you want. Next question is diameter. Now we wanted a 1/2 inch radius, so I'm going to put in a 1 inch bolt circle diameter. Then we press up arrow to go to the next question, and now it's asking for starting angle, and this establishes the rotation of our bolt pattern. 0 will put hole number 1 on positive X, but you can rotate the entire bolt pattern by using a different starting angle and align your holes different ways on your XY plane. Some common use cases for start angle would be if you're doing, let's say, a 6-hole pattern, you can choose whether the diamond of the hexagon is pointing up or sideways, or if you're doing a 4-hole pattern, you can choose between having a diamond or a square pattern. But I'm lazy, so we're going to do 0 as our starting angle. Next question is ending angle, and this one is interesting. What it means is the bolt pattern does not have to be a full circle. You can have your 6-hole pattern be on the arc of a circle if you want, or as is more common, you're probably going to want to make it an entire circle. So this is a common source of error. If your bolt pattern comes out all squished looking, this number here is probably why. So start angle was the angle of hole number 1, and this is the angle of hole number, in this case, 6. So generally what you want to do to get a complete circle is take 360 and subtract the angle between 2 of your holes. So in this case, we're going to go 360 minus 60 for 6 holes, and we're going to end up with 300 as our ending angle. So I'm going to put in 300, and that's going to give us a full 6-hole pattern on a circle. Up arrow one more time, and last question, I promise. Now it wants the number of holes in the circle, so of course that's going to be 6. And here's the magic. It's telling us from where we are now how to get to hole number 1. We just got to set these values to 0. It's telling us that we're already set on Y, so we just got to 0 out the X. And why 0? Well, what the DRO is doing is moving the origin to each hole, so that's why we always move it to 0. Now we can drill or chamfer or whatever our feature is that we're making on this pass on that location, and then press up arrow again, and there's hole number 2, and it's telling us how to get to that hole. Now we're making a hexagon here with the points horizontal, so you can see how these numbers here are going to take us up and to the left of the first hole, which was on positive X. And then we're going to drill hole number 2. Now what's cool about this is you can go back and forth between your holes with these arrows as much as you want. So for example, if you want to reduce your tool changing time, you might want to spot drill all 6 holes and then pilot drill all 6 holes and then drill and then ream and then chamfer all 6 holes. Rather than changing tools 36 times or whatever it would be, just cycle through all the holes with the first tool, and then when you get to the end, it's going to say game over, man. And then you can just hit up arrow again, go back to hole number 1, and do another lap with the next tool. And once you're done, just push this button again and try to figure out where the island went. So I'm a big fan of the bolt circle function. Now the next most useful feature is very similar, and that's the linear drilling function. It works very similarly to bolt circles, but it allows you to make a series of features along a line on your part in any orientation, which is something you do pretty often. So this feature will feel very familiar by now. You just engage the mode, and again, the first question is what plane is your line going to be in? It starts with XY, which is obviously the most common, but you could do a line in XZ or YZ if you were so inclined, but we'll go with XY here, of course. Now we need to describe the line segment that our holes are going to be on, and we have 2 options for doing that here. The first way specifies the total length of the line plus the angle where 0 is positive X. This method is the L-len mode, line length mode. Or you can go to the L-step mode and specify the distance between each feature along with the angle as before. Which one you use might be down to whichever makes more sense for you in your head, or might be based on the information you have in your drawing. So I'll use L-step mode, and let's say we want to drill 6 holes that are each a 1/2 inch apart. So I'm going to hit enter on L-step, and now it's asking us for the step size, the distance between each hole. So we want 1/2 inch. I'll put that in, hit enter there. And up arrow for the next question, and now it wants the angle off of 0, and that's positive X. Now I keep saying that positive X is 0 for all of these angles, but you're going to want to do a dry run and just double check that that's the case. Usually it's going to be positive X, and then the angle is going to be counterclockwise from positive X being your 0, but you want to double check that, and other planes of course may be different. But for this exercise we'll do a 30-degree line, so I'll just punch in 30 and enter. Next question. Now it's asking for the number of holes. We decided we want 6, so we'll enter that. And now once again it's telling us how to get to the first hole. Now this feature does not let you move the origin of the line the way that the bolt circle feature does. So the first hole is always going to say 0 and it's assuming that you were there when you started this mode. But you'll make your first hole, hit up arrow, and now it's telling us how to get to the next position, which will be half an inch away on a 30-degree slope. And now make hole number 2, and then up arrow, do number 3, and so on. And just like the bolt circle function, you can go up and down through your holes, iterate as much as you want, and then when you're all done, you get to 6, you're going to go up and it's going to tell you you're all done, but you can still go back to 1 or do another lap with another tool or whatever is easiest for this operation. And then once you're done line dancing, just push that button again to get yourself out of that honky-tonk. So that right there is going to cover 99% of the things that any hobbyist is ever going to need to know about using a DRO. When you're ready to push your DRO skills to the next level, brush up on your English and tunnel your way into the nigh-on impenetrable manuals that come with these things. The next thing you might want to look into is the SDM function, or set datum. Remember how we talked about absolute and incremental give you 2 different coordinate systems? Well, the SDM feature gives you like another 100 coordinate systems. You can use this guy to set data all over your part, anywhere that you might need to keep track of things. English sidebar. You don't really encounter the word datum a lot outside of machining nerd circles, but it's the singular form of data. So there you go. Now you can impress your friends with that little factoid at parties. Well, once we can have parties again. Another advanced thing you might look into are the tool offsets. If you're using, let's say, 5 different tools for an operation, you can tell it what the offset of each of those tools is and then call up those tools as you use them. The DRO can automatically adjust your position shown on the display for, let's say, the Z value of the end of each end mill. Now, for that to be useful, you have to have repeatable tool holding, which in a mill, in a hobby shop, you probably aren't going to have. If you're putting your end mills in collets, of course, that's not repeatable in Z. Those end mills are going to be in different places each time. But if you were going to do like a little production run, it might be worth investing in end mill holders that are repeatable in Z, and you could set them all up ahead of time and use your tool offsets. And that's my crash course on the DRO for beginners. I hope you see how powerful this tool is for what it costs and will consider one for your machine tools. Thank you very much for watching. Please consider supporting me on Patreon if you like what I'm doing here, and we'll see you next time.